Hi AP Stat students, we're about to talk about my favorite test, the chi-squared goodness of fit test. Let's dive right into it. So far we have only looked at quantitative data. Can we run hypothesis tests on categorical data? Well, on average, the new mix of colors of M&M's milk chocolate candies will contain 13% of browns and reds, 14% yellows, 16% greens, 20% oranges, and 24% blues. Imagine we had a bag of 60 M&Ms. If 13% are going to be brown and red, well, we just need 13% of 60. I'm going to jump right to my calculator to do that. So 13% of 60 will give us 7.8 of browns and reds. Now that's not really possible, so we'd probably expect that we'd have about 8 of each. Then we'd have 14% yellows, so 8.4 yellows. Then 16% greens, 20% orange, and 24% blue. So this is what we would expect to get out of 60 M&Ms, but you can see that we're not going to get 0.4, we're not going to get 0.6, and there's going to be some variation. So we could get 15, 16, 17 blue, and that wouldn't be that weird. We can get 13, 12, 11 blue, and that wouldn't be that bizarre, right? But the more M&Ms that we had, the closer that we would be to the true proportion. So I went through my niece's candy. That's a lie. I don't have a niece. And got the sample of 60 M&Ms below. So there were 9 blue, that's a little bit off. There were 8 orange, which was off a little by 4. 12 green, a little off. 15, a little off. Red, 3 off, that's pretty close. Brown, that one's the closest. So as we expect, our sample doesn't match the expected distribution, but is this difference significantly different? Our p hat of blue would be 9 out of 60. Which is 15%, but our proportion of blue was 24%. So we can run a one sample z-test to test the claim about blue candy, and we could do that for every color. We could run a z-hypothesis test on this proportion, but we don't want to do that on every color. That's going to take forever. So what we're going to look at is a test that will work to see if this entire bag matches its predicted distribution. So this is where we get a chi-square goodness of fit test. Okay, this is what it looks like. Chi is a Greek symbol. It looks like X. It's kind of where X came from, and it's chi squared. So we have our two hypotheses. There's these two, they're easy. Some people like to write these because they're conceptually a little easier. So the company's stated distribution for M&M's milk chocolate candies is correct. Our alternative hypothesis, this company's stated distribution for M&M's milk chocolate candies is not correct. Pretty easy. Or we could write it this way in the symbols. The proportion of blue is 0.24, the proportion of orange is 0.2, proportion of green, all of that. And the alternative is at least one of them is incorrect, right? It only takes one for us to not believe the stated distribution is correct. Now our conditions are a little different. The random condition is the same, right? We want a random sample. For our large sample size, we need all of the expected values greater than or equal to 5. Okay, so if we go back up to our expected values, all of these were greater than or equal to 5, so we could run this test. And we need independent samples, right? Or that 10% condition. So to perform the test, we need to use expected values given our sample size and the proportions of the null hypothesis. And what we're going to do is we use our formula for chi-squared which is the observed minus expected squared divided by expected. So what this is we have our observed 9 minus 14.4 squared divided by our expected, which was 14.4. We would calculate all of these. So this would be 8 minus 12 squared over 12 for all of them. And then you see this symbol, the sigma, it means sum. We add them all up. So once we find all these and add them all up, that is our chi-squared statistic. So I'm going to go right to my calculator and type all of this stuff in as one thing. So our chi-squared statistic, our test statistic, is 10.18. So this would be similar to like a T or a Z, right? We know in a Z-score, like 10 would be outrageous. But in chi-squared, we know it's always going to be positive because we're adding up errors, and when we square it, it'll turn out positive. So if we wanted to do each of them individually, we would see what each error would be. And let me do that real quick. So now that I actually calculated each one for you, you could see that this is going to add up to 10.18. But this yellow one was the farthest off. These were not that bad, the other ones. You can see 2.02. That one was a little bit off, and that contributed a little bit to our statistic. But this yellow one contributed the most, because this is really a measure of error. How far off were we? Okay, so now we'll need to learn a little bit more about the distribution to see what this means. So now let's look at the distribution and make this make some more sense. The chi-squared distributions are a family of distributions that take only positive values, right? Because remember it was positive when we squared it, and they're skewed to the right. A particular chi-squared distribution is specified by giving its degrees of freedom. The chi-squared goodness of fit test uses the chi-squared distribution with degrees of freedom, the number of categories minus 1. Well, we had the 6 categories, 1, 2, 3, 4, 5, 6, so this test had 5 degrees of freedom. Okay, and then if we imagine every possible sample of 60 M&Ms, when we find the chi-squared statistic of the colors, the distribution will look different dependent on the degrees of freedom. So if there's 2 degrees of freedom, let's think about what that looks like. So there's 3 categories, which means there's 2 degrees of freedom. Well, we're only adding up 3 little errors, so there's not going to be as much skewness. So we would imagine that our numbers would be closer to the expected values and closer to 0 in general. That's what this curve is, this blue line. You see how it looks like there's a chance that we could have 0 for our distribution, but our chi-squared statistic will be low. All right, there's a chance it could be pretty high, but it's still going to be pretty low. As we increase the degrees of freedom in the number of categories, there's a better chance that we would have more error. Like in ours, there were 6 categories, so this pink line, that's the distribution. Well, since there was 6 categories, we were much more likely to have more error. We had 10, which is right here on our distribution. So that's pretty rare still. Like we would expect more values around here, like 4-ish, give or take. Those wouldn't be as significant, but 10 seems like a lot of error. And then we would find the probability that we would get a result as extreme, as much error as 10 or more. That's why we would fill in this side. So when we do our distribution and we can actually find our p-value this way, our chi-squared we would draw like this, skewed. Our chi-squared was at 10.18. And so we would want to do a chi-squared CDF, right, cumulative distribution function from 10.18 to infinity with 5 degrees of freedom. I believe that's kind of what it's going to look like. Let's go to our calculator for sure. Menu, statistics, distributions. We want a chi-squared CDF from 10.18 to infinity with 5 degrees of freedom. Well, there's 0.07. So that is not really statistically significant. That's close to our 0.05, but it's not there. So this one we would say there was not enough error for us to assume that the distribution was wrong. So we cannot conclude that the company's stated distributions for M&Ms is not correct. We have a little bit of evidence saying that it's not quite these distributions based off of our sample, but there's not enough evidence for us to reject this null hypothesis. And remember, that one yellow one was the one that contributed the most. Okay, so now we're going to enter our observed values into one column and then our expected into a second, and then we'll run our chi-squared test and find the same p-value. Statistics, stat tests, chi-squared goodness of fit. So you can see that our chi-squared 10.179 was the same, and our p-value of 0.07 is exactly the same too. If we want the comp list, we can go to variables. What this means is these are the individual chi-squared values. So this was of the first one, 1.3, 0.6, 5. That 5 was the yellow one, remember, 5.2. That was the one that was the biggest chi-squared value. So if you want to do that, and you don't really have to do any of the calculations yourself at all, which is super nice. So if we were talking in general terms, the conclusion we can make is that we have some suspicion that the stated distribution of M&M color is not right, but we don't have enough evidence, we don't have significant evidence. So what we should say is, since 0.07 is greater than 0.05, we cannot conclude and then the alternative. I'm just going to say that. We've already talked about that enough.